Well, maybe we'll start. Welcome everyone. It's a real pleasure today to have Puneet Seth present. And Puneet recently joined Oxy as a senior petrophysicist in the GOM asset development team. Before that, he worked as a petrophysicist and geomechanics specialist at Shell, and there was supporting deep water GOM operations and studies. Puneet graduated from the University of Texas at Austin with a PhD in petroleum engineering, and his research at UT Austin was focused on understanding pressure interference between horizontal wells in unconventional reservoirs during stimulation and production. He has experience developing 3D field scale fracturing reservoir geomechanics simulators, and he's passionate about leveraging digital technologies such as machine learning and artificial intelligence to develop new tools. He's published his research in several conferences and journals, and it's a great pleasure to turn the floor over to Dr. Seth.
Hi, thanks, John. So first, I think I'd like to thank you and Igor for inviting me to present this talk. And just for some context, this was work done at Shell, and this study actually has been the study, I think, started more than a decade ago with the experiments and all that, around I think 2013 or so, when Shell was really starting to ramp up their water flooding efforts. So Dwayne is currently the principal technical expert for geomechanics at Shell, and he's heavily involved in Shell's water flooding operations and water flooding planning. Ronnie Hoffman is an experimental petrophysicist, senior petrophysicist who does a lot of experimental work for Shell. And John, at the time, was also senior experimental petrophysicist and geomechanicist. And he actually has developed a lot of the protocols and a lot of the workflows on how to do some of this stuff. So just for some context, the experiments and the data that will be shared in this presentation is from deep water reservoirs. It's from basically several deep water reservoirs across the globe. And we'll be using some of that data to try to explain how the stress in the reservoir changes during depletion and during re-inflation, during the re-inflation phase. And we'll also maybe talk about some of the implications of that. Again, yeah, just to clarify, I recently joined Oxy, but this was work that was done entirely at Shell in collaboration with the experimental team. Yeah, also pleased to share that we actually, the team, we won the Best Paper Award at ARMA. So always good to get that acknowledgement from the community. And if folks are interested in getting into a little bit more detail, highly encourage them to download this paper by the same name, and it's number 272. So if you search ARMA 24272 on OnePetro, you should see it. All right. Oh yeah, this one is for the lawyers. All right. So I'll start with a brief introduction of what the reservoir stress path is. I'm pretty sure a lot of you in the room or in the virtual room will be quite familiar with what it is, but I'll also maybe just give a little bit of background of why this work was important and why we decided to do this. I'll talk about the previous work that has been done in this area, looking at the reservoir stress path, and just kind of summarize what has been done already. And then I'll get into summary of the summary of results that we got from uniaxial-strain experiments that were performed at Shell over the period of 10 plus years or so. Following that, I will talk about some numerical simulations from a field scale geomechanics model that we performed, and it includes the effects of plasticity as well. And finally, I'll try to draw some conclusions or summarize some of the key highlights, the key things that we found from the study. So the reservoir stress path, sometimes colloquially or commonly also known as the depletion coefficient, or the gamma H, and depicted typically like this, like a gamma L. It's basically the ratio of change in total minimum horizontal stress with pressure change. So to understand how the stress in the reservoir changes with the pressure change in the reservoir, this is a good way to look at this ratio. If we talk about the injection phase, injection phase, for example, during water flooding, it's sometimes referred to as injection coefficient. So depletion coefficient, injection coefficient. Basically, we're looking at the stress change in the reservoir, total minimum horizontal stress change with pressure change. And it's important to look at this and try to understand this because it's important to understand or anticipate what stress changes you expect in your reservoir during long-term production and during injection, for example, during water flooding after that. And it has implications on maybe how you want to design your water flooding program or injection program, especially looking at let's say the max pressure and the max rate that you can inject in. That is directly influenced by the stress state of the reservoir, because you wouldn't want to have out of zone injection and break the cap rock and things like that. So it's important to understand how the stress in the reservoir changes first during when you deplete it and then when you start injecting. What we noticed was when we started the study was that a lot of the previous studies on this field or in this area, especially the papers that were published talking more about the injection phase, they're focused on field-based experiences, and they rely on a very limited set of in-situ stress measurements or use drilling data like ECDs, LOTs to try to interpret stress value, and then they kind of use this sparse data set. And the general conclusion from these studies that we found was that the depletion coefficient was much larger than the injection coefficient, or the stress path during depletion is much larger than the stress path during re-inflation or injection. So that's kind of what these studies said. Now, when I started doing a literature survey or literature review on the topic, what I realized was that majority of the papers and the literature out there on this topic is focused on the depletion phase. So about 90%, maybe more, of all the papers that I found on the topic were they really only talk about what happens to stress in the reservoir during the depletion phase. There are only a handful of papers that discuss the reservoir, how the reservoir stress changes during re-inflation or injection, and we realized that it's actually relatively less understood. And so one of the papers that talks about reservoir stress changes during depletion and injection, and this is one of the papers that's probably the most heavily cited in this field, is by Santarelli and others in 1998. In this paper, they talk about reservoir stress changes in the North Sea, and they determine reservoir stress from a series of mini frac tests, but also some fall-off analysis and step rate tests to get an idea of reservoir stress. Now, this paper is actually I would say, a very interesting read. So I highly recommend people interested in this area to go through this paper. But so what they talk about in this paper, just quickly go through that. They have two regions in this reservoir in the North Sea. They had a central part and then a southern part. In the central part, they've actually not talked about injection, and I don't know if they did injection, but they don't talk about the central part of the reservoir a lot, because they say it's heavily faulted, and so it's kind of hard to understand what's influencing the reservoir stress, and it's not clear. In the southern part. So in the central part, which they say is relatively less faulted, is where they focused most of the paper on. Now, what they did in this one was they had a couple of producers where they depleted to a certain amount, and then they converted those producers, they call them well A and well B, into injectors. But what is interesting is, as you can see, the data set is quite sparse, and they actually did not measure stress at final depletion. So if you look at these dots, so by the way, this is basically a plot of stress versus depletion, right? So They did not do an actual stress measurement at final depletion. That is before they converted the producers into injectors. And as you can see, this pink dot or the purple, maybe purple dot and the green dot is actually theoretical. So they've fit a line to this data, and they've extrapolated it to say, okay, this is what we think the stress will be, or what they call the fracturation pressure will be at final depletion. Then they convert these wells, well A and well B, into injectors, and they inject for a little bit. They inject pretty well. They don't inject a lot in this well B. Do inject a little bit more in this well A. And so what they basically say is that based on an extrapolation of pressures, looking at what the stress is doing in these two wells, one is going like looks okay. So based on an extrapolation, kind of averaging, so what they're doing is, okay, in this well, the stress is doing that. During injection, this well is doing that. So they kind of average it to say that looks like there is no stress recovery during injection, kind of averaging these two lines. So this is a quote from the paper: based on extrapolation of axial pressure at final depletion, injection coefficient is approximated to be 0, right? Which means that there is no stress recovery during injection. Now, the authors actually try a lot in the paper to try to explain how this could happen and why this could happen. They first turn to viscoelasticity, but then they say it doesn't really explain why this could happen or this would happen. Then they talk about elastoplasticity, trying to explain why there would be no stress recovery during injection, but then they themselves say that neither can explain why this happened. Then they turn to an explanation. They say that this is maybe because of behavior of rocks at large scale. I found that to be a little bit of hand wavy explanation without any kind of backing using a field scale model or anything like that. So there was really no evidence to this statement that this might be due to behavior of rocks at large scale. And then they themselves say that this behavior has never been observed during extensive rock mechanics testing of cores from this field. So they never saw that in the experiments that they conducted from cores in this field. The second paper is from Davison and others in 2016. In this one, they look at minimum horizontal stress based on actually drilling data, so like ECDs and LOTs and FITs in the 4Ds field in this in the North Sea. They also look at a field in the South China Sea, and in there, to get an estimate of minimum horizontal stress, they look at step rate tests. So what they see in the North Sea, they see that a depletion coefficient of around 0.43 and an injection coefficient of 0.25. So already they say that injection coefficient based on field data looks like can be non-zero. In South China Sea, they look at 3 zones: depletion coefficient of around 0.9, injection coefficient of 0.3. In the 2 zones, and then in the third zone they say it's 0. For this, they try to explain this by doing a more Coulomb kind of failure analysis and saying that there was shear failure that happened, which could explain this, but this was not very clear to me why this would be the case. Main point being that there was, again, in this work, there was no actual stress measurement that was done at final depletion before injection, and so the evidence is not very compelling on, like, if you don't know what the actual stress is at final depletion, it's very hard to say what happened at final depletion and then during injection. And most of these measurements in this paper and even in the Santarelli paper are actually they're actually using drilling data or something like fall-off analysis or strep rate tests to get an estimate of minimum horizontal stress. We don't think that's the most reliable way to get an estimate of minimum horizontal stress. We'd rather do a mini frac test or something like, in the unconventional world, like a DFIT or something like that, and look at the closure pressure and all that. So this is what I found on the a couple of papers I found. One of them very heavily cited. Based on field experience on what happens during to the reservoir stress during depletion and injection. Now, there are also papers that have done some experiments, and they talk about they look at the same thing, change in stress of the sample during depletion and injection. Now, important thing to mention here is all of these experiments, 1, 2, and 3 in these papers they're actually done on either synthetically manufactured sandstone, or they're done on like benchmark cores like the Castlegate core here. So the first one by Runa Holt and others was published in 2016, in which they synthetically prepared samples. They prepared some stiff samples, so relatively low porosity, and they also prepared softer samples with the higher porosity. And in the stiff sample, they see a depletion coefficient of 0.4, injection coefficient a little bit lower than that, 0.4. But in the paper itself, they're not happy with the results from this test because they mentioned there was some issue with the bonding agent when they were trying to prepare this sample or these samples. And so they calculated the injection coefficient to be something according to them should be closer to the depletion coefficient. But anyway, they mentioned that there was some issue with how the sample was created. What is very interesting is in the soft sample or the higher porosity, much higher porosity sample, they see a depletion coefficient of 0.47 and an injection coefficient that is actually higher than the depletion coefficient, right? Second one, Rafipour et al. This was work done, I believe, in collaboration with BP and I think University of Tulsa. So in this one, the focus of this paper is a little bit different. They try to look at different boundary conditions, how different boundary conditions would impact the depletion and injection coefficients. What I've showcased here is the uniax-strain boundary condition, which is most representative of the GOM reservoirs. In this one, they see, so they have a Castlegate core, which is 90% quad, so quite stiff, I imagine, have a depletion coefficient of 0.85, injection coefficient, not only non-zero, but also quite close to the depletion coefficient, right? And so this is basically this is what happens to the horizontal stress during depletion, and this is what happens during injection. So you can see that there is some stress recovery during injection. This third one is an experiment that was performed at the University of Houston by Prakash, and he was a PhD student in Mike Meyer's group, and I think George Wong's group. This was a study that was funded by Shell. In this one, they actually took they created a sand pack from Florida beach sand, which they say is of the same provenance as some of the deep water GOM reservoirs. Now, this, of course, as you can imagine, is basically a sand pack, so it's quite soft and unconsolidated. In this one, they actually did multiple cycles of depletion injection. Let's just focus on the first one. They saw a depletion coefficient of 0.4, and look at that, injection coefficient of 0.7, which is actually higher than the depletion coefficient. So what we're seeing in experiments here is, as you can see, is quite different from what was observed using drilling data or follow-up analysis, step rate tests in the field, where experiments are showing that there is stress recovery during injection. Okay, so this was kind of a long history, or like a long summary of the previous work that was done. Let's now get into the work that was done in this study. So I'll share the results from 100 uniaxial strain pore volume compressibility tests or compaction tests that were conducted on both consolidated and unconsolidated cores. And these cores were acquired, as I said, from deep water, from Shell's deep water fields from across the globe. There are two kinds of tests that were done. The first one is a UPVC, also you can say it's a constant pore pressure effective stress protocol. What happens in this one is the pore pressure is held constant and the axial stress is increased under a uniaxial strain condition to mimic the increase in effective stresses during depletion. The second type of test is a true pore pressure depletion test, in which the pore pressure of the core plug is actually depleted and then brought back to the original condition. I'm not going to get into more details of what these protocols are for the UPVC and the UPPD, or the constant pore pressure effective stress protocol, or the true pore pressure depletion protocol. But John, who was also on this call and co-author of this paper, has actually published a paper which is referenced. And if you look at this paper, you'll see that in the references. So if you're interested in what this protocol is, what the setup was like, and how it works, highly recommend going and reading John's paper from 2016. So as I said, so 100 tests on both consolidated and unconsolidated. Most were done on consolidated, 79 were done on consolidated rocks or consolidated samples, 21 were done on unconsolidated. And so we measured many things like compressibility, all that, but also looked at the reservoir stress path during both depletion and reinjection. And so what we see from the results, or the summary of the results, is that the injection coefficient is non-zero. So that's number one. And there is actually stress recovery during when you're injecting or the reservoir is being reinflated, right? What is very interesting is what we saw, that for stiff rocks or consolidated rocks, the injection coefficient is actually very similar to the depletion coefficient, sometimes almost exactly the same. For unconsolidated or soft rocks, the injection coefficient is actually higher than the depletion coefficient. So this is a summary of the tests. As I said, 79 were consolidated, 21 unconsolidated. This is a distribution of which ones were with one protocol versus the other, the true pore pressure versus the constant pore pressure effective stress. This is the range of the ratio of the injection and the depletion coefficients. And as you can see for the consolidated tests, it's hovering close to the number one. And if you look at the mode of the data, it's quite close to one. So meaning that the injection coefficient is almost the same as depletion coefficient. For unconsolidated, it's hovering quite a bit higher than one, meaning that the injection coefficient is actually, and if you look at the mode of the data, it's larger than one, meaning injection coefficient is larger than depletion coefficient, which is very different from what we saw in the papers from Santarelli and Davison. Okay, so just to explain what was observed in these tests, I'm going to use one example from consolidated and one from unconsolidated. The plots that you see here basically show a stress on the Y, depletion on the X, strain on the Y, depletion on the X, and same for the unconsolidated sample. So what we see is for the in case of the consolidated sample, the depletion or the stress change during depletion and reinflation. Sorry, so depletion is these circles and reinflation is these triangles. So the stress change for a consolidated sample during depletion and reinflation is kind of overlapping basically, and so the ratio of the injection to depletion coefficient is actually quite close to 1.01 in this case. Also very interesting to see on the strain side of things. So if you look at strain versus depletion, so this is depletion, this is reinflation. So what we see is in consolidated, or what we saw in consolidated samples, was that most of the strain was elastic and was recovered during injection. That is not the case, however, in soft unconsolidated rocks, where, as you can see, there's quite a like if you look at the slope of these lines, it's very different for depletion and reinflation. And as you can see, if you take a ratio of these numbers of the slopes, 0.5 to 0.4, so the depletion to injection to depletion coefficient is actually much larger than one. It's 1.18 in this case. Also very interesting to see on the strain side of things, if you look at the strain versus depletion, most of the strain in case of soft unconsolidated samples is actually plastic, meaning it's not recovered during injection, right? So why do we see this, right? So why is this happening? Why do we have a similar injection and depletion coefficient in case of harder or stiffer consolidated rocks versus softer unconsolidated rocks? I'll explain that in the next example. So there were some tests where we did progressive cycles of depletion and reinflation, meaning that we did multiple cycles. So this is, for example, cycle 1, 2, and 3. So what in cycle 1, the sample was depleted to a certain pressure and then reinflated back to the original pressure. In cycle 2, some of the depletion in the first cycle is retraced, but then the sample is subjected to a higher depletion than the first cycle and then reinflated back. Cycle 3, again, retraces the depletion in cycle 2, but then extends or subjects the sample to a higher depletion than it has previously observed, and then it's reinflated back. So what are the key observations from this experiment with progressive cycles of depletion and reinflation? The first one I would say which is very interesting, is If you look at the reservoir stress path coefficient or the injection coefficient, in all of these cases is actually very similar. So 0.57, 0.54, 0.56. So one could say it's around 0.55, 0.56 or so on an average. Very, very similar, right? The second thing that is also extremely interesting is whenever whenever we are retracing the depletion in a previous cycle, so that would be this part in cycle 2, where we're basically going through the same depletion as the sample had previously seen in cycle 1. And here, where basically this part of depletion, which is retracing the depletion that the sample had already seen in cycle 2, the depletion coefficient is very similar. And so it's actually the same and is very similar to the injection coefficient, right? So this is very interesting. Only when the sample is subjected to a depletion that it has not seen before. So obviously in the first time you're depleting, it's the first time it sees that depletion, the depletion coefficient is different. Again here, whenever new depletion that was not seen in the previous cycle is performed or sample is subjected to that, the depletion coefficient is much lower. Same here. Whenever it sees new depletion, the depletion coefficient is much lower. And very important thing, this is also again a unconsolidated sample, right? So what is going on here, right? The explanation is sort of goes like this. So when the sample is subjected to loads that it has not experienced before, both elastic and plastic deformation are occurring. And in case of unconsolidated rocks, plastic deformation actually can dominate depending upon how much depletion you subject the sample to. And so you're seeing this decrease in the depletion coefficient whenever that happens. Whenever new depletion happens or sample is subjected to higher effective stresses than it was subjected to before. In contrast, whenever the sample experiences loads that it had already experienced before, so that would be in all of the injection cases, right? So what we're doing in injection is re-inflating, reducing those effective stresses. So it's basically all of those stresses the sample has already seen before during the depletion phase. So whenever the sample experiences loads that it has already experienced, the elastic deformation, so basically it's recovering that elastic deformation that happened. So elastic deformation dominates, and this results in a reservoir stress path coefficient or a depletion or injection coefficient, depending upon what you're looking at, that is larger compared to when both elastic and plastic deformations are occurring, right? So basically, whenever you see significant plastic deformation, the depletion coefficient decreases. When you're injecting, you're reducing the effective stresses, and the sample is basically just going through stresses it has already seen before, and it's basically recovering whatever elastic component of deformation was, it's recovering that. So you see those straight lines. Now, this will become even more clear when I talk a little bit about linear elastic model versus elastoplastic and what we did with numerical simulation. So we created a 3D field scale finite element model, and it was a relatively simple model, meaning like an elliptical reservoir with shale over, side, and underburdens. The dimensions of this were such that it's laterally much longer than the height. So the ratio of height to the lateral extent or the lateral dimension is very low, meaning it's a very long, thin reservoir, which is very representative of GOM reservoirs. Also, to simplify the results, this was a 3D model, right? But the results were taken from the center of the reservoir, because, I mean, one could show the results set everywhere in the reservoir and it would be like a nice 3D plot and everything. But we decided to just focus on like one point in the reservoir. So we can actually compare the results from here to what we are seeing in the experiments, right? Looked at two different constitutive laws. First, we did the simpler linear elastic model. And this was basically, we did this to just as a gut check to make sure the model is working fine and the results that we are getting make sense before moving on to the elastoplastic CAM clay model. Now, as many of you will be familiar, if we have a linear elastic system with a constant total overburden stress, it can be analytically derived actually that the injection coefficient is equal to the depletion coefficient, and it can be analytically expressed as a ratio of Poisson's ratio in this form: 1 minus 2 nu by 1 minus nu. And so this is so based on the parameters used in this model, if you assume a linear elastic model and use this analytical equation, the depletion coefficient or injection coefficient was 0.57. This was the results from the model. And as you can see, the depletion and injection coefficient are actually exactly overlapping because we are assuming linear elastic model. There's no plastic, nothing going on right now. So the depletion and injection, also all of the deformation was elastic, which is recovered during injection. And so the depletion and injection coefficient are the same, and they're quite close to the analytical solution as it should be. So this was a good gut check on if the model is working fine and so on. So this was the first thing we did, was linear elastic. Then we incorporated elastoplastic model, the CAM-CLAY model, and try to see. And the reason we did this was not to actually match a particular experiment or a particular test, but it was more of a conceptual exercise to understand how plasticity is affecting the depletion and injection coefficients, and what happens at more of like a reservoir scale instead of a core plug scale. That was the intent of doing the numerical simulation. So what's going on? So this is a PQ plot. So mean effective stress on the X, generalized shear stress on the Y-axis. And we start here in the elastic region. So this is the yield surface. So the sample starts at this point. You start depleting. And during that, so before the sample reaches the yield surface, which is when the plastic deformation would start happening. So this is the elastic regime. When we're in the elastic regime, you see the depletion coefficient is this number, 0.56. When we get to the yield surface, plastic failure begins, and the yield surface progressively moves with further depletion. And this is the final yield surface. And you can see this is very different from what's happening here. And also very interesting, the depletion coefficients. See, when the plastic failure begins, when it reaches that yield surface, the depletion coefficient is much lower than what was observed when elastic deformation was dominating. What happens during re-inflation? We're basically decreasing the effective stresses, and as you would expect, the injection coefficient is the same as, since this is elastic deformation, injection coefficient is the same as depletion coefficient when the sample was in elastic regime. So you get the same value. On the strain side of things, it's also very clear what's going on. This is depletion in the elastic regime. Plastic deformation starts to dominate. You see a clear change in the strain versus depletion. During injection, again, we see that the slope of this line is basically the slope of this line because we are recovering elastic deformation. So to conclude, based on the results of 100 uniaxial strain compaction tests on both consolidated and unconsolidated cores, it was quite clear that for consolidated rocks, the injection and depletion coefficient is very similar, sometimes even exactly the same. And that's because in harder consolidated rocks, it is elastic deformation that dominates. In softer unconsolidated rocks, the injection coefficient can be actually higher than the depletion coefficient. The reason is plastic deformation, depending upon how much you deplete the sample, plastic deformation can dominate. And when that happens, the depletion coefficient decreases, as you saw with that curving that in that example that I showed previously. Modeling results that we presented agree with observations that we saw in the experiments. And this is what I just said. This means that there can be, so this is the main point kind of this study, is that this means that there can be significant stress recovery during injection or inflation, which is very different from what was previously published based on field-based studies with sparse data sets and different techniques used to estimate stress, which was Santarelli and some other papers. So what are the implications? So this is very interesting, right? So the implications, why this is important is Now we know that, okay, you should expect stress recovery during injection or re-inflation. What this means is that we can avoid some of those very or overly conservative designs during planning of an injection project, be it water flooding or CO2 injection. And what I mean by that is, since we know that there will be some stress recovery, you can maybe inject more, or you can have less conservative rates of injection and max pressure of injection, because you know that the stress is going to be recovered. This is the main thing, because before this study, a common conception or misconception was that there is little to no stress recovery during injection operations. With that, I want to thank Shell for allowing us to publish this and release this material publicly, and happy to answer any questions at this time from the audience. Thank you.
Thank you, Puneet. Very, very informative set of experiments and considerations. We do have a couple of questions, and folks have been trying to answer them online, but maybe we'll just bring it out into the public. And so Ed Siebritz has been asking whether in the cyclic depletion lab tests, cycle 1 depletion also looks nonlinear, so it would be good to break 2 slopes.
That's right. Good point. Yes. Yeah.
So do you want to elaborate on that?
Yeah, it is curving. That's right. I mean, so even as you can see, so this would have been, I imagine, quite a soft sample, and that you're depleting to, let's say, what is this, 2300 psi, and you see that curving. So maybe it was elastic up to maybe this point or so, and then the plastic deformation started dominating, and that's why it does that. So yeah, good point. We maybe should have separated it out, but yeah.
A quick comment.
Agree.
From John Dudley. Cohesionless materials are basically nonlinear. So
yeah,
there's really no elastic. There's very, very little elastic behavior in any of these cohesionless. I have never seen linear behavior in a depletion experiment on a cohesionless material, which is what this experiment is.
So
maybe one other point. Hey, this is Dwayne Michalczyk, another co-author. We weren't trying to suggest that the plastic deformation was necessarily linear, right? We were just using it as a reference point to compare with the inflation period, right? That's why we only drew one line. We're just trying to make the point that if you just stick a line through the depletion period, you'll always get a lower slope or lower gamma rates than the re-inflation part, right?
Yeah. Thanks, Dwayne. So I also want to point out that as we look at this plot and several other plots in the paper, maybe having one line. So for softer or unconsolidated rocks, as both John and Dwayne mentioned, it's not maybe enough to have a single line as your depletion coefficient. As you can clearly see, it's curving. So this is something that we've clearly stated in the paper as well.
Very good. And Safdar has an interesting question. He's wondering if you made any measurements on porosity or permeability enhancement on these samples during injection.
So this is John Dudley. These tests are all university or uniaxial pore volume compressibility tests. They were done specifically to measure the uniaxial pore volume compressibility. So yes, they all have porosity data. And many of them, in fact, did have both horizontal and vertical permeability measurements during depletion and inflation.
Yeah. Did you?
Maybe just one other point. This is Dwayne here. There's a whole nother story which we didn't delve into on whether you want to call it porosity change on depletion versus re-inflation, or whether you want to call it pore volume compressibility change on depletion versus re-inflation. It's similar in the sense that when you're depleting, you're getting both plastic and elastic pore volume change, and then when you re-inject, you're only getting elastic pore volume recovery, right? And that ends up leading to, at least for unconsolidated cases, much lower pore volume compressibility values on reinflation compared to depletion.
Indeed.
Mike, can you hear me?
Yes.
Yes, absolutely. Because my understanding is when you have this plastic deformation, it's hard to regain that porosity. So I'm interested to see, you are showing that especially in the unconsolidated samples, when you have a higher injection coefficient that you're showing, does it mean that there is enhancement of the porosity?
No. It's just the opposite. That's what I was trying to say.
Okay. Yeah, exactly. Okay.
Because you're only recovering the linear elastic deformation, which is smaller than the plastic one, right? So you don't recover hardly any porosity.
Okay.
Yeah.
Okay, got it. Thank you.
This is Sid Green. Very, very nice presentation, nice results and a very interesting topic. It seems to me that how you get to the reservoir stresses before you start your depletion or reinflation measurements would be critical, particularly if you look at unconsolidated or weakly consolidated material, that is the lower strength, stiffness and strength materials. So how you get there is awfully important, I would think. And so I assume maybe you've picked a particular route to get there, to get to your reservoir stresses and simply stuck with that. But to me, that would be very important, I would think. The second thing I would speculate, maybe you have some information you could comment, but I would think that the compressibility of the pore fluid might also affect this depletion and then recompression parameters that you're measuring too. I don't know if you have any information on that or not. For example, if you have a pore fluid that has certain gas in it or lower compressibility, I would think that would have an effect on the. But anyway, very nice presentation.
Yeah, thanks. And I think,
Sid,
sorry,
I'll
go on,
take
John.
this.
Yeah.
I'll take this, Puneet.
Yeah.
All these tests are essentially run by the protocols in the IRSM suggested method that's been published. So samples were taken up to in-situ stress generally by raising them isostatically up to the horizontal stress and then adding the vertical stress. That's the probably the most common way we get things there. One thing that's important to monitor is the deformation that takes when you get there. If you get a lot of deformation, then the sample is likely to be disturbed, and we just didn't run those experiments or didn't report them. So it is important, to take the sample to in-situ stress conditions. How you get there will affect things. And it's important to actually monitor the deformation going there, particularly in these unconsolidated samples, to decide whether or not your sample is essentially disturbed. The second point is all of these samples are drained experiments. Almost all of them are done with most of them are done with synthetic brine, synthetic reservoir brine, but some of them, in some cases, were also done with a non-reactive oil in cases where we were concerned where the brine might be affecting the grain contents. Maybe you had shales you didn't know about in there, or some cases, some of these samples had halite or something else that could be dissolved if we didn't get the brine composition exactly right.
John, I guess that also as you're getting to reservoir stresses, how you control the pore pressure, I guess, is critical. You could just do an undrained test, but I agree with everything you said. You're picking one protocol. I don't share enthusiasm that necessarily is going to apply that or give you the right depletion and compaction, or the re-inflation compaction or reduced compaction
All I
necessarily.
can say, Sid, is
But
that
one has to pick
measurements
a
we've
given
made on
protocol.
samples have been duplicated by measurements in the field on both compressibility and on in-situ reservoir compaction.
Hey, maybe one thing to add, this is Dwayne Miklinchuk again. Puneet, if you'll go back to the numerical results with the Cam Clay slide. You know, like Puneet said, this numerical modeling was conceptual, right? We weren't trying to match a test. And, you know, for an unconsolidated sample, you know, pretty much at the beginning, you would be at yielding, right? And so we didn't do that because we wanted to be able to show what it looks like elastically and how it changes. So we designed this sort of numerical experiment. You know, maybe it's a bit artificial, but we designed it to have enough depletion stages to see what linear elastic looked like and then what plasticity looked like, right? So that it's a bit artificial in that sense, but it was a conceptual model.
And I think Dwayne, I'll let you answer this if you want, but on the question of gas, I do remember there was something that was done, but I don't think it's publicly released on what we saw. So if you want, I'd say you can answer it. If not, that's fine too. On what happened on the CO2 side with the same kind of trying to investigate what happens when you inject. So I don't know. I think it's not publicly released though. So but there's certainly people looking at what happens when you inject CO2 to the stresses in the reservoir. So I'll leave it at that.
I think John covered that point, Puneet. He was saying that this is all drain behavior, right? So the pore fluid shouldn't matter.
Okay, good. Yeah.
Anyone else?
I emphasize again, very nice presentation.
Thanks. Thank you, Sid.
Sid, I couldn't agree more. This was a great presentation, and thank you, Puneet, and thanks to your co-authors. I mean, we made this a lively engagement, and it's a really important topic. And thanks for showing us some fantastic data.
Thank you. No, happy to present, and I would like to thank my co-authors as well for letting me get involved in this thing. They had been doing this for many years before I joined the company. So yeah, really, yeah, just very thankful that I was able to become a part of this. And yeah, and thanks Dwayne for letting me, you know, I'm switching over to this side of things and still letting me present this. So that was really cool. Thanks.
So just we'll end Safdar. This correct me if I'm wrong, Puneet. This was ARMA 212?
272.
272 in 2024.
That's right.
And that'll be available on One Petro. Anyways, thanks all.
Can you repeat the number, please, once again?
272.
272.
Yeah.
Okay, ARMA.
Right here. If you search ARMA 24272, this should show up.
Okay, wonderful. Thank you very much.
And there was a question. This presentation will be available. It has been recorded.
Yeah, this is all publicly released material. So yes, yeah.
So Puneet, that was great. I really enjoyed that.
Thanks, John. Good to hear from you again, and Dwayne, you as well. So
yeah, well done, Puneet.
Yeah.
Thanks, Dwayne. Thank you.
You know, as someone who started their career in soil mechanics, I really appreciate this topic. It's everything sort of falls together.
Thanks, John.
Okay, so we'll see everyone. Thanks again.
Yeah, thanks,
Thank you.
Puneet. I think it was a nice presentation.
Hey,
Hi. I was actually also, I mean, I started my career also in soil mechanics, so definitely I join John in that kind of appreciation as well. I mean, mostly typically we have been using the depletion coefficient to be higher than the injection coefficient.
Yes.
I mean, of course, the slope is one thing, but what about the actual stress reversal, the horizontal stress? Does it, so if the injection coefficient is higher than the depletion one, then are you saying that the horizontal stress is actually higher after the reinflation than what it was before?
I know the answer to that, but I'll let Dwayne answer this because
Yeah,
I don't know if he,
it is. Actually,
it
the
is, yes.
experiments show
So
that as well.
I'm just being super careful now, Dwayne. So,
Yeah, no,
but
it does
yeah,
show that,
yeah, okay, great.
Okay, thanks. Sure.
Thanks.
Yeah, thank you.
See ya.
Thanks.
All right,
Bye bye.
bye.